We are more than pleased to have Professor Nigel Hitchin from Oxford, who is going to give us 2 lectures. So let me just mention that Nigel is one of the famous British duo, here Hitchin and Donaldson, who made gauge theory an art, and that led to many fantastic works. So he was instrumental in developing generalized geometries, things related to geometric Lagrange program, so-called Hitchin component in the modular space, which has been subject of very serious research, and also very strong results connected with A and P branes, connected to the modular space of Higgs bundles, as you all know, Ungar symmetry is subject of some interest here in Miami. So the next week will be a week of complete celebration of all influences of Nigel to different areas of mathematics. So we'll hear more about all these topics. But today we'll just discuss Spinor-valued Higgs bundles. Nigel.
Thank you. And thanks very much for the invitation to give these talks, but also for this next week's activities. Humbled by the fact that they're taking place. So this is the first of 2 lectures I'm going to give, and since next week it's supposed to be 50 years of my mathematics, actually, these are the first 2 papers I published. 1974, but I suppose the idea is that I'd already read them in 1973. So I thought as a topic, not as a topic, but as a kind of motivation of the 2 talks I give, I would think of these 2 things. So the first one is about spinors, and so that's basically based on my thesis. And the second one is about, as you see, 4-dimensional Einstein manifolds. So my second talk will be about as well. Not in any sense following on from these, but it's just that I've retained an interest in these 2 things over 50 years. So let's start with spinors. So this is the sort of thing that I was looking at in my thesis. So in general, if you have a manifold M, which satisfies this topological condition, this spin condition, the second Spinor-valued class should be 0, then that admits a spin structure, which means you can construct a certain vector bundle over it, a spinor bundle, and an associated elliptic differential operator, the Dirac operator. And in even dimensions, this space of spinors splits up into what nowadays we would say positive chirality and negative chirality spinors, the plus part and the minus part. And the Dirac operator goes from one to the other. And this is like the fundamental example of an elliptic operator which underlies the index theorem, the LTS index theorem. So, but what I'm going to talk about today is a kind of minor version of that. What happens if you take a manifold to be a Riemann surface, 2-dimensional manifold? Then this second Spinor-valued class is just the first germ class mod 2, or the Euler characteristic mod 2, which is obviously 0. And so it is a spin manifold. And so what is a spin structure? So we have this on any Riemann surface, any algebraic curve. I'm calling it C now because we think of this as an algebraic curve. Then we have this holomorphic line bundle of complex forms. So locally, we're looking at complex valued 1 forms, the form of like dx beside dy, or lambda dz, where z is a local coordinate. And these, as we go around the curve, define a line bundle, the holomorphic line bundle, this the canonical bundle. Okay, bundle of holomorphic 1 forms. And a spin structure, in this case, is a line bundle whose tensor product with itself is isomorphic to K. Now, that is not quite the same as a spin structure in general, because there's a rather sophisticated notion of equivalence of spin structures. It's not, I mean, the same underlying C infinity bundle can represent two different spin structures. But in the case of a compact Riemann surface, that difference is captured by the holomorphic structure. So basically, a spin structure is a holomorphic square root of the canonical. And that's a kind of basic feature of spinors, that spinors, tensor spinors, are differential forms. So the spinors themselves are somewhat mysterious objects. I always think, ever since 50 years ago, there's still something mysterious about spinors. But if you look at tensor products of them, then they become something which we can relate to more geometrically, namely forms. It's what physicists call field sync, bilinears of spinors are actually. Okay, so this is what a spin structure is in 2 dimensions. And the Dirac operator, apart from a square root of 2, is effectively the d-bar operator. So we look at the space of C infinity sections of the spin bundle. This is now one of those half spin bundles, k to the half. And it goes to the other side, which is, in terms of the holomorphic structure, the d-bar operator, which goes into sections of k to the half, and k bar. It looks literally like this. So this is the complex conjugate that we can use as well. And so if we're looking at solutions to the Dirac operator, it's just the same as looking at holomorphic sections of this square root of the canonical. And now there's one feature about this Dirac operator here, that if we take a spinor, so psi1 is a section of k to the half, we apply d bar to another one, psi2, then we get a section of k tensor k bar, so it's k to the half times k to the half times k bar. So this is just the same as these are just the same as 2 forms on the curve, and so on the Riemann surface. So you can integrate these. So if you use Stokes theorem, you see that you get this. So that formally, this d-bar operator, this Dirac operator, is skew adjoint. We can say a little bit more than that. So if you choose, so far all we've done is use the conformal structure on the surface, or the holomorphic structure. If you choose a Riemannian metric, which is compatible with that conformal structure, then you can identify the right-hand side, which was this thing, k to the half k bar, with k bar to the half. And then this is the d-bar operator is going from sections of one bundle to sections of this complex conjugate. So what you can say is that it's an antilinear skew-adjoint operator. So that puts it in the realm of the Thier-Singer mod 2 index theorem. And this happens in dimensions 8k plus 2, that this dimension of this vector space, modulo 2, is a deformation invariant. It's the first thing to say, and can be represented, in fact, by a topological characteristic class, KO theory. Well, that's not going to be the more sophisticated aspect of it. It's not going to be here. But one of the things that happens is that if you're doing the algebraic geometry of curves, you have a line bundle, you want to know how many holomorphic sections there are, you want to know the dimension of H0, and one way that helps you usually is the Riemann-Roch theorem, which gives you the difference between H0 and H1. In this case, Riemann-Roch gives you nothing, so there's no information about whether there are holomorphic sections of this. But what the information we do have is that we know whether they are odd or even. So what about this? So these square roots, we can always tensor a line bundle k to the half, whose square is the canonical bundle, by a line bundle whose square is trivial. And so there are 2 to the 2g spin structures, square roots. And it turns out that the dimension is, this is even, sorry, is odd for this number of them, and even for the remaining ones, g minus 1 times 2 g plus 1. So this is, okay, so this is like 19th century mathematics in terms of a differential operator, but anyway, the result is well known. You know, if you ask how can we try and recognize what these sections are, how can we bring them back into the real world of differential forms, well, you can take tensor products. So if you have a section of k to the half, and square it, and you get a section of k, and so you get a holomorphic differential, but it has double zeros. Wherever s has a zero, it has a double zero, s squared. And so that means that some, at least the geometrical interpretation of the sections. So here's the sort of thing you can do. So if you look at the canonical map from the curve into this projective space, so this is the projective space of the vector space, which is dual the space of differentials. So this is basically take a point in C and look at the evaluation map of a section at that point, or in concrete terms, if you take a basis of differentials and write them out as local holomorphic functions, that's the way you get this map into projective space. Then S squared is a section of the canonical bundle which has double zeros, and that means it's in this setup it's a hyperplane which is tangential to the image. So in low dimensions, low degrees, sorry, low genus, I should say, then we get some familiar bits of classical geometry. So when genus is 2, this number is 6. These are the 6 Weierstrass points on the curve. So it's, if you have the 6 points over P1, then we take the branch cover over to get the genus 2 curve. But if genus is 3, and it's the canonical map, it embeds it as a quartic surface in P2, then this number is 28, and these are the famous 28 line tangents, the same quartic curve. And if you have a genus 4 curve, the generic one is a cubic and intersect on cubic and quadric, then you get 120 tritangent planes. So these are interesting numbers. In fact, okay, so if you haven't seen a quartic with 28 line tangents, here's the picture. I won't leave the picture long enough for you to count them, but the interesting thing is that the configuration of these bitangents relates to the Weil group of type E7. If you like, if you change the parameters of the quartic curve, follow the lines around bitangents, then you get a permutation of these bitangents, which is a permutation which lies in this E7 Weil group. Similarly, 120 tritangent planes on the 8 Weil group. So that's the classical geometry related to spinors. And that's not quite what I want to talk about, but a related problem as well. But what I should point out before we move on is that what we just saw was that for a plane quartic curve, so a curve of genus 3, if it's a plane quartic, it has these 28 square roots with one section, and it has 36 square roots with no section filled. On the other hand, if you take a rather exceptional type of curve, you take a hyperelliptic curve of genus 3, so that's a double covering of P1 branched over 8 points instead of 6. Then this object here is a differential with double zeros. So these instead of having 36 square roots with no section, you now have one with a two-dimensional space of sections. So A and B, this is the square of a section k to the half. So if you like, AX plus B and the square root of this is a section k to the 12, where there's two parameters A and B. So there's one square root which has the two-dimensional space section. So there is, if we consider a family of curves, not just a family of objects, but a family of genus curves, then it's possible that this dimension will jump from its generic value, in this case 0, to 2. So but it will always jump to try an even number, because the parity remains fixed. Okay, so now let's move on to, so that was essentially, let's say, 19th century mathematics. So let me move on to what are now called Higgs fields. You may ask me what relationship these have to physical Higgs field. That's something which I don't want to go into. There is a kind of tenuous relationship, otherwise we wouldn't use this name. But it's not something which is very relevant to what I'm going to say. So now we introduce a holomorphic vector bundle. And then so what's now being called a classical Higgs field. So this is the sort of thing which developed about 35 years ago, is to consider a holomorphic section of not the canonical bundle, but canonical bundle tensor with the endomorphism of V. So this is this is, if you like, a locally holomorphic matrix valued function differentials. Instead of looking at this, what I want to consider is a Spinor-valued Higgs field, title of my talk, which is where we replace the canonical bundle here by a square root of the canonical bundle. So everything looks very similar, but as you see, there are some essential differences. So why do I want to do this? Big question. Well, partially it's curiosity, I suppose. Partially it's because of my kind of long-standing interest in spinors. But actually there's a recent paper here, physics paper, or physics-based paper, which introduces some object which I don't fully understand. But what you see here is that the authors here talk about E tilde valued G Higgs bundle. So here they're taking instead of taking endomorphisms twisted with a canonical bundle, they're taking triples of endomorphisms twisted with 3 bundles, and each of these is k to the Ri over 2. So they're introducing the idea of half integer spin. So a classical Higgs bundle, that's what they call it in their paper, is where Ri is equal to 2. But now they're saying let's look at Ri varying and looking at the Higgs bundles relative to Higgs. Now, don't ask me why they're doing it here, but a little bit further down in the paper, they look at what they're calling the equivariant Verlinder formula. And this is a formula where as you see, they make this particular remark here, that a k to the R over 2 valued Higgs field contributes this factor. And as you see, when R is equal to 1, this factor disappears. So my suspicion is that the paper is really concerned with Ri being greater than 1, where things maybe look very similar to the classical situation. But that means that maybe it's more interesting to look at the case R equals 1, which is what I'm talking about today. So that's one reason for maybe investigating this. Another is that a long time ago, actually it was at the time that I was writing first papers on Higgs bundles, I had a student at Oxford who wrote his thesis, which included a section on this sort of thing, and included this configuration of points and lines. And later on, I'll tell you what this is. These are points and lines in projective time space. So Bill didn't stay in academic mathematics, but anyway, his thesis was an interesting exercise. So here's the situation then. So if we look at the classical situation, if we twist with the canonical bundle, then Riemann-Roch theorem and Serre duality tell us that the difference between space we're looking at. So here I'm introducing 0. So it's convenient really to get rid of the abelian part and to look at trace-free endomorphisms and to look at vector bundles where we fix the top exterior power. That's really like saying that, well, in all of these situations we can always tensor by a line bundle, add a line bundle, add a multiple scalar to the endomorphism. Let's remove that and look at the essential non-abelian part of it. So in this case, what we get if E is of rank n, then this is the dimension of this difference. And so we always know that there are homomorphic sections. We have, if you like, an inequality on the sections. And if the bundle is stable, so we'll say what that is in a minute, then there are no non-trivial endomorphisms of the bundle. So we get exactly this number of k-twisted Higgs fields. On the other hand, as I pointed out in the case where we just have k to the half, Riemann Roch gives us nothing. So maybe there are no non-zero Higgs fields. It's possible that if we take a bundle, a nice bundle, a stable bundle, then we may not be able to find any of these k to the half Spinor-valued Higgs fields. On the other hand, we're looking at Higgs fields with values in endomorphisms, twisted endomorphisms. Then the trace phi1, phi2 is a non-degenerate symmetric form on this pattern. And under those situations, the mod 2 index theorem holds with spinors with values in something which has a non-degenerate symmetric form. So what that means is that the bar operator becomes formally skew adjoint again because of this using a trace. And as a consequence, we have a mod 2 invariant, which we can use. So sometimes you can relate it to the parity of the k to the half itself. So for example, if the rank is 2 and this is trivial, then if you like, the statement that this is a deformation invariant means that we can deform the complex structure on E to a trivial complex structure. And then this is just 3 copies of the input bar. I should say that I should have put the trace-free part there. So the trace-free part of this is 3-dimensional. So 3 is odd, and so the parity of that is the same as the parity of this itself. So there's some way in which we can usually relate the parity of k to the half. Okay, so but now we have this question which I just raised. Start with a nice family of vector bundles like moduli space stable bundles. It's possible that at some point on this we don't have any Higgs fields twisted with k to the half. So we need to have some means of not just relying on a previous existence theorem about moduli space bundles, but we need to have some more direct way of constructing these objects. So we learned from the classical Higgs moduli space how to do that. So let me first of all talk about stability here. So holomorphic bundle on this curve is stable if for each subbundle the slope, as it's called, the degree of F divided by its rank is less than the degree of the slope of E itself. When you have stable bundles, then there's a nice compact moduli space whose dimension is given by this. If we fix the top exterior power, this is the dimension. And these are very interesting varieties. In some sense, we know a lot about them. We know their cohomology, we know relations in their cohomology, thanks to some important work a long time ago. But actually, what they are individually is not so well known. Especially, what is known is some of the cases in low genus. So the classical one is the rank is 2 and the genus is 2. then in the case where the determinant is trivial, then the moduli space is projective 3 space. And in the case where it's odd degree, so you might as well fix it to be a line bundle driven by a point, then it's isomorphic to the intersection of two quadrics in P5. And the tangent space at a point in this moduli space is given by this sheaf homology group. By Serre duality, this space of Higgs bundles, can now be interpreted as the cotangent space for the moduli space of stable bundles at this point. So we have here an interpretation of this space of Higgs bundles, Higgs fields on a given vector bundle in terms of the bundle is stable in terms of the cotangent space of the point corresponding to the moduli space. So now you can this was introduced over 30 years ago. You can look at a joint stability condition. If you look at a pair of objects, a vector bundle E and the Higgs field phi, then you can ask that the pair is stable if we restrict this stability condition, this slope stability condition, to subbundles which are invariant under phi. And then you get a moduli space, a non-compact moduli space, which certainly includes the cotangent bundle of M itself, because if the bundle itself is stable, then any Higgs field would be stable with it as a pair. So the whole of the cotangent space at that point is actually part of this space. So on the other hand, there are extra points where the underlying bundle is unstable, but nevertheless the pair is stable. So there's a large open set, which is this total space of the cotangent bundle, but there are lower dimensional pieces which you can add on to make this Higgs moduli space. And then there's another way of looking at this where we can forget completely about stable bundles and look at it from another point of view. So if we take now the characteristic polynomial of the Higgs field, it's now a polynomial like this where the coefficients are invariant polynomials in phi of various degrees. Well, here at degree 1, degree 2, etc., right down to the determinant, minus the determinant. But phi was now, if you like, a matrix with values in the canonical bundle. So these are all sections of powers of the canonical bundle. Put them all together, and it gives us a map from this moduli space, which has dimension, let's call it 2m to Cn, which is actually a proper map. And not only that, but the generic fiber is actually an abelian variety. It's a torus, so you can look at if you like, to each phi, you can associate the eigenspace bundle. If you like, this equation tells you that there's a single valued eigenvalue x on this curve. If you pull back the bundle curve, x is a well-defined eigenvalue, and you look at the eigenspace corresponding to phi, well, actually to phi transpose, and that is a line bundle on S. And more importantly, you can do it conversely. So if you start with a curve, well, let's say it's a smooth curve to begin with, and the line bundle on it, then there's a way of constructing a Higgs bundle on the C itself. You take the direct image sheaf of the line bundle. So what that means is that for each open set in C, you look at the holomorphic sections of L on the inverse image. So at a generic point, the inverse image consists of n copies of mu, and then clearly the holomorphic sections of that are like holomorphic maps into an n-dimensional vector space. So this gives you this direct image construction gives you a vector bundle. And what was X? Well, X was really a section of the pullback of the canonical bundle on S. And so if you multiply by that, you get a map from the sections of E over U to sections of E tensor K over U, which is the Higgs field. And so this is a way of constructing Higgs bundles, classical Higgs bundles, shall I say, from an algebraic curve with a line bundle. So we don't mention anything about starting with the bundle itself and trying to construct a Higgs field from that. And of course, so given that, we can replace the canonical bundle by k to the half to get Higgs fields twisted by k to the half. So we can always do this. We can always find such curves. And, this is the way that you can construct these Spinor-valued Higgs fields. So you can define a space in the same way by looking at this stability condition, this paired stability condition. But now there's a proper map to direct sum of powers of the k to the half. So it's a smaller base. And if you look at the dimension of the whole space, then it's given by the formula, which is the dimension of the moduli space of stable bundles plus 1. So this brings it down to something which is much closer to stable bundles. So what happens here? Well, if this is an odd case, the dimension is odd, and now we say if he is stable, then generically this over the moduli space of stable bundles, this dimension is 1. So what we get is a one-dimensional space for each point on the moduli space of stable bundles, at least for those where the dimension is equal to 1 and not equal to 3 or more. Now, the expected codimension of this jump is actually 3. So you have to think about these expected dimensions in terms of kind of finite analog of this. So the odd and the even case is rather like looking at, so let's say the even case is rather like looking at skew symmetric forms on an even dimensional vector space. Then generically it's non-degenerate, but if the determinant vanishes, then, which is a single condition, that's when you get degeneracy. On the other hand, if it's odd, that's like looking at a skew symmetric form and an odd number of variables. That always has one. So generic situation is where there's a one-dimensional space, but then it might jump to 3. And so the model there should be that, for example, if you look at skew forms in 3 dimensions, then they become degenerate when its form is 0, which is codimension 3. So the codimensions are reflected in the finite dimensional picture. Anyway, in this case, if the expected codimension is achieved, if it's the dimension greater than or equal to 3, then this line bundle over an open set in the moduli space, where this is equal to 1, this will extend onto the whole space. And then you can identify it by using, you can identify it with the square root of the canonical bundle of M itself. So M always has a spin structure, and in fact it's this. So this identification is via, like, Grothendieck, Riemann, Roch, and the fact that the multiples of the first Chern class are what in that direction, not the first Chern class, but the Picard group is just the Z of these moduli spaces. So here we have what I think of as an analog. We have the K-twisted Higgs bundles give us a moduli space which includes the total space of the cotangent bundle. Our k to the half twisted Higgs bundles have a moduli space which is has an open set, which is the square root of the canonical bundle. Moduli space.
So K-twisted means usual.
K to, yes, what I've been calling classical ones, I have to say, yeah. So there's a difference though. As I say, that in this case, the identification of the cotangent bundle is local, it's kind of canonical. In this case, at the moment at least, it occurs because of this is a line bundle of a particular first Chern class. There's only one such line bundle in that two class. So it's kind of topological argument. It's not quite so direct. So, but nevertheless, it's really kind of remarkable that if you take the curve and look at holomorphic one forms as the twist, then what you get are holomorphic one forms over here, holomorphic spinors here.
So, I mean, according to a theorem, where you tell us this classical Higgs bundles correspond to the representations of the fundamental group, what do these things correspond to?
Yeah, well, okay, so maybe it's the Diracian category, and maybe that means that there's some. Yeah, I don't think it works that way.
I think.
There are links.
No, we do have Diracian categories because the product of two like that is going to be like that.
Yeah,
so,
that's right. But then you can argue that it should be something different. Okay, so what about the even case? So that was the odd case. Right? The odd case gave us a line bundle. What about the even case? So if it's even, then this is the case where generically this is zero. So for most stable bundles, we don't get any Spinor-valued Higgs bundles. So, and the dimension jumps to greater than or equal to 2 in codimension 1. So, and where does it jump? So that's because we've got this skew joint operator that because the index is 0, the bar operator, the Riemann rock gives you 0, that means there's a canonical determinant section of the Quillen line made. But because the d-bar operator is skew symmetric, that is actually the square of something. So again, it's like saying that the determinant of an even symmetric matrix is the square of something. It's like saying but this works in this context as well. There's instead of there being a determinant section, there's a Pfaffian section of the square root. So the Pfaffian, what I call the Pfaffian is the jumping locus in this case, is a divisor of canonical bundle to the minus the half. So what we get here is that, I call it P. So P is this Pfaffian divisor. Then this Spinor-valued moduli space on a big open set is looking like a rank 2 vector bundle over this divisor. Of course, the dimension is still dimension n plus 1 because we go down one dimension and then up to 2 dimensions. So, what do we know about this vector bundle? The rank 2 vector bundle. When we had a line bundle, we could say exactly what it was. It was this k to the half. In this case, well, we've got a 2-dimensional space of Spinor-valued Higgs fields. So we can take the bracket open, and that will give us a classical sphere. So I claim that this is actually, so this is a cotangent vector. I claim that this is co-normal to that point. I'll give you a little proof of it. So what that means is that we can certainly identify the top exterior power of P as the canonical one, square root of the canonical bundle M restricted to P, because we understand P is the 0 set of the section of P through. And so, okay, so I say that this is a conormal one. There's an argument to prove this. It's a conormal vector. So here we have, so let's take a tangent vector through this Pfaffian hypersurface. And so this is an element of, so we represent that in Dolbeau terms by 0, 1 form of colors and it's a tangent vector to this. So these two Spinor-valued Higgs fields, they deform along P. That means as we vary the holomorphic structure, we can vary psi I. So they satisfy an equation like this. So there's a variation in each psi I dot. And now if we evaluate this tangent vector on bracket, so that's the cotangent vector I just constructed, then you can use the bracket, the properties of the Lie bracket, and then you can use these equations like this. You can rewrite it like this, and then Stokes theorem is zero. So this bracket here annihilates the tangent vectors to this nice way. Okay, but that doesn't tell us. That just tells us that what the top exterior power of this vector bundle is. If we want to get more information about it, then here's one way of doing it. So if I take something in the dual space as a space of differentials, then I take my Spinor-valued Higgs field, it traces chi squared with my alpha to it, and then I get so what do I get? I get a quadratic form on this two-dimensional space here. So this quadratic form has two. Okay, here I've said line bundles. Okay, what I mean, actually, this must be an old version. Okay, it's two subspaces of V, two null vectors, and they will coincide where, so we can look at this another way. If we take this class here in H1, we multiply it by this one here, it goes over into here. So this is another way of writing that quadratic form. It's a map from V in dual. And we know what the top exterior power is. So what we get is that the determinant of alpha is a section of kn to the minus 1. So these two subspaces, they agree where this is equal to 0, which is this that defines it here. And now here's an alternative point of view. So we take the same description of this quadratic form. Now we can say this is a homogeneous quadratic on this vector bundle. It's the same thing as saying it's a section of the second exterior power of the dual. And that, since we know what the top, if you relate V to its dual, just two-dimensional by introducing the top power, so it's like this. So if you like, this is like a kind of Higgs field, if you like. It's an endomorphism of this rank 2 vector bundle over the moduli space of stable bundles, or actually it's not. It's on the Pfaffian, really, but with values in k to the minus half. So from this point of view, these L1 and L2 are eigenspaces of this endomorphism. So this tells us how we ought to think about this. And if you take a double covering branched over this determinant of 0, and then the vector bundle, assuming that everything is smooth, this vector bundle is the direct image of the line bundle, and this double covering. This is like the spectral covering of a Higgs field. On the other hand, if you look at the canonical bundle of this, if you're taking a double covering, then it's actually trivial. So this is the direct image of a line bundle on the RBL. Well, it may not be a manifold because P may have singularities, probably will have singularities. So this is a curious fact which I'm not sure what to do with. But it's there is this vector bundle here. Something we should say about it in terms of line bundles and RBL. Okay, so in the last quarter of an hour, I want to look at three things. One is the question of are there any links between the Spinor-valued Higgs bundle and the classical Higgs bundle? I want to look at some low genus examples, and then I want to look at this question of jumping of dimension, because that in fact always would bring in singularities, which is kind of a bad thing. So what about the links to the classical Higgs bundle? Well, here's one. So suppose that both of these are odd, both the k to the half and endomorphisms of k to the half. Then we can take a section here, fix it, and And then for any Spinor-valued Higgs field, we can multiply by S and get a section of this. So this is again spinors, tensor spinors are formed, except one of the spinors is matrix value. So then you get and this gives us an embedding of the spinor moduli space inside the Higgs moduli space. And so this image lies inside what's called the critical locus of the integrable system. I haven't mentioned that word, but the integral system of the moduli space of Higgs moduli. So it's the point where this derivative of this map is suggested. So the curve that you get here is actually a normalization of the spectrum curve of the classical Higgs. The other
Is it the component?
no, it's no. So what it is, you might ask what it is. It's so the critical locus is actually a symplectic submanifold, symplectic submanifold of M, and this is a
Coisotropic.
It's coisotropic in the induced symplectic structure. It's not coisotropic in the big space, but coisotropic. So the other one, the kind of marginal one, is something which appears in the literature under what's called the Cayley correspondence. So this is where you're looking at the non-abelian Hodge correspondence, which relates flat connections with classical Higgs bundles. So here's a particular situation of this Cayley correspondence, and that is that if you're looking at flat connections with holonomy in this real group, and you want to understand how to describe them by a classical Higgs bundle, then you take a Higgs bundle, which is the direct sum of the vector modulus dual, and you take a Higgs field, which is off diagonal, if you like. A takes B to be dual, B takes the other way around, these are symmetry. But in the case, and then there's an integer involved in this, which is basically the degree of B. This tells you that actually these representation spaces have their own components. But in one case, if the degree of this is equal to the degree of this, then there's a component where this B is actually an isomorphism. And if you look at this component, then that means that you can reduce this whole question here to ordinary Higgs bundles with values in k squared. But obviously you can, if you replace k by k to the half, if we look at like Higgs bundles with this shape, but with values in k to the half, then the moduli space is going to be ordinary. So that's saying that some rather exceptional types of Spinor-valued Higgs bundles actually can be realized in ordinary Higgs bundles. Okay, what about examples? I've always felt that it's always good to put examples. So let's look at curve of genus 2, bundle of rank 2, where degree 0. So I said that the moduli space here of stable bundles is given by the projective free space. So the way it appears is that you look at the line bundles of degree 1 on C, such that the tensor product with E has a non-zero section. Then this gives you a divisor inside the Jacobian, essentially. And then this P3 is the projective space of this four-dimensional space of divisors. And now suppose we take, so we're looking at the case where k to the half is odd. Then if it's odd, then in the genus 2 case, it means that actually A1 is one of these bias stress points, then actually it's k to the half. So the six odd ones are given by the 6 bias stress points. So this is a situation where, okay, so this implies that this is odd. So that's right. So if we take an odd one here, and this is the even degree, then this is odd. So then what we get is an inclusion, if we multiply by section S, as I said before, we're looking at an inclusion of km and a inside the cotangent bundle N. So we have this line bundle inside N. And what is what? So the space is P3. The canonical bundle of that is O minus 4. So this is an embedding of O minus 2 inside the cotangent bundle of P3. So what is it? At least that's the question I ask myself. So I'll give you tell you what it is. Okay. So if you choose a basis, there's a nice basis you can choose of this in terms of natural basis of theta functions. And then what we have is this action of line bundles of order 2 given by tensoring. So tensoring with a line bundle of order 2 doesn't change the top exterior power. And in this basis, the group is generated by double transpositions and double sign changes. You have these 4 coordinates. So P1, P whatever, P1, P2, you look at double transpositions and double sign changes. This is this action, this group. So now we take this model for the cotangent bundle P3. It's basically writing it as a symplectic quotient. So it's a space of pairs PQ, Q not equal to 0, PQ equal to 0. So in this case, it's the sum of PI and QI, because we chose this particular basis. We divide that by C star. So the Q's, Q not equal to 0, the Q's you can regard as homogeneous coordinates on P3, and the P's as coordinates in the cotangent plane. So then what I claim is that if you look at this matrix, this transformation, and then you'll see that this is skew symmetric with respect to this inner product. And so that means that we have this relation here. So it actually gives us a conception, or at least a map from the P3 into the cotangent space in that model at each point, because it's homogeneous degree 2 as well. And so that is the way O minus 2 is embedded in this T star P3. You can also think of it perhaps this way. If you look at the Euler sequence, then you take the A is skew symmetric, so it's a map from wedge 2 of this to this. So how do we work that one out? So maybe there's a better way, but at least we have this. There's a beautiful formula by these physicists, Minsky and his student, some time ago about the genus 2 integrable system. So they have a formula for it. So this is the map from the cotangent bundle P3 to the space of quadratic differentials, given by that trace phi squared, and it looks like this. So if you don't like the denominator, you can write it this way, and this is the quadratic differential. So, and these coefficients here, these Rij's, look like this. So then, what happens is that if we look at trace phi 1, phi 2, then evaluated x1, that's a quadratic form obtained by putting x equal to x1 in this formula. Now, if this phi 2 was the sort that we're taking our section S, which vanishes at x1, and any psi here, any phi here, then we're going to get 0 here. So for all phi. So this quadratic form is actually degenerate at this point. So if we put x1 equal to 0, we get a degenerate quadratic form. And then you just look at this formula and you see that degeneracy. Maybe there's a better way of saying that. But so for each of these six Weierstrass stress points, there's a copy of O minus 2 inside the cotangent space of P3. And in this case, if we look at it from the other point of view, there's a map from this 4-dimensional moduli space of Spinor-valued Higgs bundles to sections of the canonical bundle, 2-dimensional. The generic fiber is an abelian surface. And it's so it's in fact in this case I talked earlier on about line bundles and Jacobians. Actually, these are prim varieties. So it's not full Jacobian spectral curve; it's a prim variety. But in this case, the abelian surface is actually the Jacobian of a hyperelliptic curve, a genus 2 curve, where if you like, you replace the x1 by the a. So looking at the inverse image of a holomorphic one form, which looks like this. Holomorphic one form vanishes at the a, and then if you look at the projection onto P3 of these abelian surfaces, well, strictly speaking, I suppose it's a rational map, then what you get is a chromavariety, which is a quartic surface in P3. So now if you look at the other situation, suppose you look at the same curve, same bundle, but now you take an even spin structure. So what are the even spin structures? They are obtained by taking these 6 bias points and breaking them up into 2 copies of 2 disjoint copies of 3.
Is this actually correct? I mean, so these prim varieties, they don't seem to have a principle polarization. Maybe you want to say that they're isogenous.
I think in this case, this is a case where actually it is principally polarized. Yes, so if you look in the big thick yellow book, you find that this is
But it's a ramified cover.
yes, a ramified cover is you read 2. I think that's the situation where actually the prim can be principally polarized. I think actually, when I gave this talk in front of Ron said, "Oh, it's all."
Oh yeah, I won't give you a passport.
So these even spin structures are given by, so there are 10 of these. So there are, if you think about it, there are 10 different ways of choosing disjoint pairs out of 6. So in this case, this is the case where this is generic to 0. So in this case, so we have this Pfaffian divisor, which is now a quadratic surface in P3. And so what we're looking at is now we're looking at a double covering of this quadratic surface, which is P1 cross P1, branched over a full 4 curve. So P tilde is a K3 surface. So what we're saying is this vector bundle over the quadratic is the vector of the line bundle on the K3 surface, which is so. And we know what the complex theory of tau is. What I claim is that actually it's the second Schoen class of the 0 range. So basically the line bundle we're looking at is, has this property that the involution on the covering takes it to its dual C1 L squared is equal to 0. So I'm not quite sure how to see this. Some of you in the audience may know this better. As I understand it, the equilateral was this type K3 looks like 2 hyperbolics plus a dihedral P18. One of these is the pullback of the H2 plus P1. So if we got this, and we're looking at something over here, this square is equal to 0. So, and we can have a plus 2 and this minus 2. Anyway, that's I'm not quite sure what it is. You would guess that it was the kind of minimal one. Anyway, that's the picture in that situation. And in this case, the generic fiber in this abelian vibration is this is a product of elliptic curves. So you take it now. You take the holomorphic one form, just like this, and then the elliptic curves are like this. So we've got 3 here, 3 here. So you look at 2 elliptic curves, and then project onto P1. So as you might expect, you need 4 projections into this. Okay, back to the make a few more minutes.
Yeah.
So this is now one of the problems. So what I've said is that there's a jumping here. So if it jumps from 0 to 2, codimension 1, and what I've said is that this is a codimension vector. Similarly, if this is odd, then it jumps from 1 to 3, and here you can take these brackets as well, and as you might expect, the same argument says that these are 3 conormal vectors, which, if they're linear independent, are they? This is corresponds to the expected codimension speed. But it doesn't always happen. So the first example in 1, actually there's a curve of such. It's a jumping curve. But example 1 was the case of P3, and that's rather special because the semi-stable locus appears as small part of that. So maybe that's the reason for that. But anyway, the expected dimension is not always codimension 3. Well, the expected one is, but the actual dimension is what you can do is you can work out what the cohomology class should be. This cycle, this codimension 3D cycle. So people know what the standard generators in rank 2 of the cohomology are, then it's also given by these Chern classes. And in genus 2, it's a 3-dimensional space, an intersection of the 2 quadrics, then this jumping locus is equal to 8 points. So, and this is where I finished with this diagram. So this is in Roxbury's thesis, actually in the title page. So this is these are the 8 points that appear here. So these are 8 points in P5. They lie on and these lines, you know, these 16 lines here, running them, 4 going through each point, and that is that's what it looks like in this case. So the jumping locus is here. For those who know about it, the wobbly locus consists of these lines. It's a beautiful picture, and what Roxbury points out is that actually these 16 points correspond to the points in this group. So this is a picture, if you like, tensoring with a line bundle order 2 on one of these gives us one of these 16 points. And he describes the multiplication law on these by following Griffiths and Harris points. So it's in there somewhere. Not exactly. So I better start there. If you want to, if anyone wants to, I can tell them what the line, what the vector manipulation is. I think maybe this is where I should start.
Thank you very much. Questions?
The completed moduli spaces that are non-complete, what do they look like on the boundary?
Yeah. So I don't know. So okay. So whenever we get this this jumping locus, we'll introduce singularities. If you look at if you just look at finite dimensional model, you know, if you look at say a skew form in 3 variables, then pairs of objects, which is a vector skew form. It's effectively the same as looking at a pair of elements in the Lie algebra of SL2, which pairs commuting pair. That has this singularity. So we're always going to have these singularities, and actually completion of these things, that there is a kind of standard way of completing what we call by doing multiplying by C star and dividing out at a certain level. But even in the case of classical Higgs bundles, that hasn't been used very much. I mean, there is a standard compactification due to how Riemann yourselves. But for me, the problem with these spaces is this singularity. So in the case of Higgs bundles, classical Higgs bundles, you still get jumping in the dimension of the space of Higgs fields, but that's counterbalanced by the same jump in the automorphisms, basically. So that can even out. I mean, the singularities are not very bad because, if you like, because the dimension of the space of the Riemann rock says the dimension of the space of morphism minus the dimension of the space of Higgs fields is fixed. So if one jumps up, the other one jumps up, and more things to divide out by, and so you get much more chance of having some points or good tangent space. This situation is this. I mean, you don't see it very much in this flow genus case because so there's an issue there about what kind of space this really is. On the other hand, the intriguing thing is that this total space of the line k to the half appears, but it doesn't. At the moment, it just appears because of topology. On the other hand, this square root has a role to play. This it corresponds to what's called the critical level. So there's a commutative sheaf of differential operators on the sheaf of sections of k to the half. It appears in this work of Valence and others, quantization efficiencies. So there's something very special about this k to the half, which comes from a different angle, but which makes it special not just because it has a particular first jump mass. I wonder whether there's some link between that property, this critical level, and what we're doing here. But I have no idea where it goes.
Other questions?
Are there any additional geometric structures on this model space?
Yeah, that's a good point. Right, so the other one was symplectic homomorphism. And this one, well, the case of the total space of k to the half, that does have a holomorphic volume form. Well, not volume form. So the holomorphic fixed dimension n is a holomorphic n form, which vanishes on the zero section. So again, if you look at the canonical bundle of this total space, and you look at the pullback of there's a tautological section of the pullback of k to the half, and that actually. So, but it doesn't come in the same way. So it's not kind of locally determined by understanding pairing between tangent vectors and cotangent vectors. It's a little bit beyond first Chern-Class issues, but there's some which you can kind of describe, but I'm not sure whether they might be zero. That's one obvious question. I mean, you can construct a moduli space analytically just by using the same type of equations, gauge theoretic equations, as the standard Higgs bundles, but you have to introduce a metric to do it. So it's not, and then that's so the metric that's put on the moduli space, smooth place of the moduli space using that is not really, it doesn't depend only on the holomorphic structure. You can make a choice. So there are a lot of things which are different. So I don't really know quite where this sits.
Other questions? So is there a Turelli theorem which tells you that out of this split model of specific bundles you can have
I see, how does it work?
classical meaning you have a Jacobian and a Dirac right, and out of this incorrect
Yeah, sorry. What's that? No, I'm thinking about the work that this was in his collaborators. They looked at the moduli space. But I think they reduce it to a question about modelized basis state functions. So here, yeah, so actually,
Into the some component of the bivalent signal.
yeah, but then this things go wrong. Things go more wrong with this. One thing I could also say is that if you look at these quadratic functions, so what I've said is that we're looking at this total space of k to the r, and we have this quadratic map to holomorphic, let's say holomorphic sections. Quadratic map. So what is a quadratic map on the total space of a line vector? It's a section of the square of this the cube of this. So it's basically, if this is quadratic, then and this gives us holomorphic sections on the total space. Well, it gives the holomorphic sections of k to the minus 1. So we have that's rather like saying in the classical Higgs bundle that these invariants give us holomorphic sections of the symmetric square of the tangent line. So we get a g-dimensional space whereas in the classical situation, this gives us all possible the ones which are obtained this way give us all possible sections of this symmetric square. In this case, they don't, because I mean you can even see it in the case of anyway, we have the Verlinder formula in general, which gives us a formula for sections of k to the minus 1 over n, and it's the space of sections is much bigger than g. So there's another difference. On the other hand, of course, we have a number of square roots. So maybe if you take square roots, you'll get enough sections. But I think it's unlikely. And you'll get up by putting so what I'm saying is that for each square root, looking at these Spinor-valued Higgs fields here, you get holomorphic sections of k to the minus 1, but then it's the same k to the minus 1 where the square roots.
So how does the discriminant depend on the even or odd theta characteristic?
Yeah, so it will, in fact, yeah, well, it's so here, so well, the geometry is, the choice, take this one, the choice of the square root gives you, which one is this? Anyway, it gives you, it gives you the, where are we? Maybe this is not a good example.
Well, at least I mean,
yeah, in this case, the choice of the square root gives you different map here, it gives you 6 different maps from minus 2. So that is, right, so that's 6, but then there are a lot more maps from minus 2. Yeah, so it's, I don't know how central it is, but it's there looking at it. It's intriguing.
all right, let's thank Nigel again for the